question revision video for GCSE exponential graph. So the question is, we have to draw a graph of a curve y equals 2 to the power of x for various values using this graph paper they supply, and then we use it to find the solutions to a couple of problems, or questions really. So we're asked to draw the graph of values of x from -2 to 2. First of all, we need to find some points, and the obvious thing is to draw the points for all the relevant integers. In fact, without a calculator, we'd struggle to do anything else. So we'll calculate those in a moment. We need to remember while we're calculating them that a to the power of -n equals 1 over a to the n. So a negative index means we do 1 over. Okay, for part B, we need the y value when x is equal to 1.4, because our curve is y equals 2 to the x, so 2 to the 1.4 means we're putting an x value of 1.4 in. And for this, we will draw part of the line x equals 1.4, see where it crosses the curve in the y direction, and proceed from there. For part C, it's sort of the other way round. We need the x value for when y is 1.4, so we'll draw a cross by drawing the line y equals 1.4 and see where it hits the curve in the x direction. And because we're using the graph to solve equations, the bigger we can draw it, the better. This will mean using as much of the graph as we can, and it will make it more accurate. Okay, so let's get on with calculating those values. So we want x values of -2, -1, etc. So if x is -2, that means we have 2 to the power of -2. And remembering what happens with negative indices, that means we have 1 over 2 squared, and that is of course a quarter. For -1, we have 2 to the power of -1, and that's simply 1 over 2 to the 1, or just a half. 2 to the power of 0, well, anything to the power of 0 is equal to 1, although you may want to think about 0 to the power of 0, but not in this question. That's just a thinking thing for another time. 2 to the power of 1 is just 2, anything to the power of 1 is itself, and 2 squared is of course 4. So this means we have the following points, expressed as decimals now because we're working on a decimal type of grid. For the x-axis, now I mentioned that we need to make the graph as big as possible for the maximum accuracy. So for the x-axis, we've got 4 large squares in the negative and the positive directions. So that means because we only need to go up to +2 and down to -2, we can give 2 large squares per unit. And notice that first I put in the whole numbers and then I put the halves in, or the 0.5s and 1.5s in. So we've got all our references there. For the y-axis, we have 4 large squares in the negative, not in the negative direction. There's a mistake on the slide there, but never mind. We have 4 large squares in the positive direction. All our y values are positive, so that's okay. But that means we can only give 1 large square per unit. So 1, 2, 3, 4 like that. Okay, and don't forget to put your indicators on the axes to show where these numbers are referring to. So on the x-axis there they are, and on the y-axis. Okay, so the next thing to do is to draw the points in, and here they are as if by magic, and we can see we've got -2, 0.25 on the left, and then we've got -1 with 0.5 as a height, or the y value for the next point, and so on. And then finally we need to draw the curve, and some people find it easier to draw a smooth curve if you rotate the paper sort of upside down, and then the way your arm sweeps round will follow the curve. You may want to give that a try. And there we have the curve drawn. And one really important thing to remember is don't use a ruler when you're drawing curves. Otherwise, it's not a curve. Okay, so we have our graph drawn, and now we can get on to part B, and we need to find the y value when x is 1.4. So for this we draw part of the line x is 1.4, see where it hits the curve in the y direction by then drawing across to the y-axis. So in this case obviously we do use a ruler. So there's the line going up from x equals 1.4, and then it goes across and hits the y-axis there. And from the graph we can see that 2 to the power of 1.4 is roughly 2.6, a little bit over 2.6, but we can't really give a second decimal point in this situation. For part C we need the x value when y is 1.4, so we do the sort of reverse process. We draw part of the line y equals 1.4, see where it hits the curve by dropping down. So there we have the line going across from y equals 1.4, and then down it goes. And we can see that the solution to 2 to the x is 1.4 is about 0.5. Now, in fact, if you go on to study A-level maths, you'll be able to calculate these values, and it turns out that 2 to the power of 1.4 is 2.6390 to 4 decimal places, so that was reasonably accurate from the graph. And the solution to 2 to the power of x equals 1.4 is 0.4854, so again, reasonably accurate. Okay, we've got a couple of alternative questions in this video. These are questions you could be asked. You could be asked to use your graph to find the gradient of the curve at a particular point. So we're going to see what the gradient is at x equals 0.5. So the first thing we need to do is to draw a tangent to the point, I should say to the point, not at the point, to the point on the curve where x is equal to 0.5. So there we are, we've done our best effort. Obviously we've used a ruler, slightly wobbly ruler by the look of it, but there we are. And the next thing we need to do is to find the gradient. So the gradient for a line is the change in y divided by the change in x, or you may have been told rise over run. And to do this on a graph we need to make a triangle, and in this case, because our numbers are quite small, we could do a triangle where the baseline is 1 unit in the x direction, so then the change in x, or the run, will be 1, and that will save us having to do any division, which is quite nice on a non-calculator paper. So there is our triangle, and you can see it goes from 0.6 up to 1.6 in the x direction, so that is indeed a length of 1. So all we have to do is to find out what the rise of the triangle is, and it's going from 1.5 up to 2.5, so the rise is just those two subtracted, so 2.5 take away 1.5 is 1, and that means the gradient is about 1. Doesn't look like it's 1, but that's because our axes aren't equal lengths. Okay, and as with the previous question, if you study A-level you'll be able to calculate this sort of gradient, and this one happens to be 0.9803 to 4 decimal places, which again is reasonably accurate. We have a second alternative question, another thing you could be asked, and this one is use the trapezium rule with 3 ordinates to estimate the area bounded by the curve, the x-axis, the y-axis, and the line x equals 2. So our thinking for this is, if we're only asked for 3 ordinates, then between 0 and 2, because we're using the y-axis or x equals 0, that's the same thing, then we use the values x equals 0, x equals 1, and x equals 2. We draw up to the curve from these x values, and then we join the tops of the lines to form trapezia. So we're going to get 2 trapezia here. There's the lines going up, and that's the tops of the lines joined up, and we can see we've got 2 trapezia next to each other. And the trapezium rule is we do a half of the x gap, so that's the distance between the x lines that are going up from the axis, and then we do the first y point plus y value rather plus the last y value, and then 2 times the y value that's in between. So putting numbers in, we've got a half times 1, the x cap is 1, we're going from 0 to 1 and then 1 to 2. And the first y value is 1, the last y value is 4, and the y value in the middle, in this case just the 1 value. If you had more ordinates, obviously you'd have more y values in between, but in this case the value in between, it has a y value of 2, so that's the height above the point x equals 1, where we've drawn up from x equals 1. Okay, so those are our numbers. We're going to tidy that bracket up. 2 times 2 is 4, plus the 4 plus the 1 gives us 9, so we have a half times 1 times 9, and that means we can say that the area is roughly 4.5, and notice the squiggly equals, because obviously this isn't terribly accurate. In fact, we can see from the diagram, the graph, that this will be an overestimate. Those little slithers above the curve are excess to the area under the curve. And again, if you study A-level maths, you'll be able to calculate this area. And it turns out the area under the actual curve, as opposed to the trapezia, is 4.3281 to 4 decimal places. But again, we can see that our estimate is not bad. So depending on what we wanted to find the value for, what problem we were trying to solve or information we were trying to gain, we wouldn't be too far out by using the Trapezium rule. And of course, if we used more ordinates, then it would be more accurate.